Okay, gut.
Recording is on.
Hi, welcome to this presentation of our results, which we call autoencoder-based kernel ICA, nonlinear blind source separation. Our team consists of me, Christian Reimers, Benedikt Heidrich, and Xavi Andoni Tibau Alberdi. So we tackled the problem from as a blind source separation problem. So let me talk about blind source separation first. In blind source separation, we normally have multiple sources, here represented by musical instruments. And the signals of these sources mix, and we can only observe the mixture. The task in blind source separation is to separate this mixture again into the different sources. Here, for example, the musical instruments. In our case, of course, the sources are the volcanic activity and the solar activity. And the mixture is the output of the temperature series outputted by the climate model. In the example that you see on the screen here, the mixture is linear. Therefore, the problem reduces down to an independent component analysis, or ICA. In our case, on the other hand, we are quite sure that the mixture is nonlinear and very complex, and that a simple ICA cannot tackle it or solve it. Therefore, we came up with a different method. The idea is to first train an autoencoder similar to a kernel function. So a kernel is a known method to make nonlinear relationships linear, or in a different space. And a kernel is normally a scalar product evaluated on not the examples, but an image of the examples under some feature function. And this feature function is trained or learned by the autoencoder in our case. So we train an autoencoder and use then the encoding at the bottleneck and perform ICA over this encoding. For our experiments, we used an autoencoder with a bottleneck size of 32, but this is a hyperparameter that we need to optimize. So let's come to some results. The first component of our ICA normally corresponded to the volcanic activity, since it seems to be the strongest signal. And the second component was related to the solar radiation. Here we see the correlation. So in blue we see the output of our ICA. In orange we see the ground truth for the volcanic activity. The correlation is only 0.49, but as you can see, we have a very good way of identifying whether there is volcanic activation by checking whether the value of the ICA gets negative. Hence, the correlation is maybe not the best metric, and we could have reported way stronger results on a different metric. We reported correlation as the basic metric. We think that it's important to come up with better and stronger matrices, but we didn't have the time to do it. For the second component, here we see the correlation to the solar radiation. We smoothed the signals. So since we expect the climate model to have a lot of variation, internal variation, we smoothed it with a filter over 19 years, and to match, we also smoothed the solar radiation over the same period. As you can see, the correlation is 0.41, and you can see the signals here. The next thing we did was to split the whole area into subregions, as we expect the signal near the equator to be stronger than at the poles. And the results can be seen here. So here we see the first component of a fast ACI after 32 bottleneck autoencoder only trained on the equator region. And as you can see, the correlation is higher. And again, we have this very nice effect that the value of the ICA component is only negative if there is a volcanic outbreak or volcanic activity. We observe similar thing for the solar radiation. Here we take the different area, which is the pole in this case, the South Pole, and we observe a high correlation between the second component of our ICA and the solar radiation of 0.49. Of course, this was only a 1.5 days, and therefore we didn't manage to do most of the stuff we actually wanted to do. The first thing is we only used one of the time series for our calculations and for calculating stuff, and we left the other for test, and we actually planned on making really severe tests and being able to check whether our methods generalize over this one example to the other. And of course, building autoencoders is always hard. Many architectures can be used, and we for sure haven't found the best yet. Our actual goal was to use a beta variational autoencoder, since it does the autoencoder and the ICA part together in one go. We also thought about using other climate model data, not just the temperature data, but other data, just to train a stronger autoencoder. One of the main drawbacks we found was that all we did so far was using autoencoders that translate one image to another image, when we are actually quite sure that the main part of the signals actually can only be discovered in time. Therefore, we think that the valuable future work would be to consider multiple time steps. As baselines, we considered also not just ICA, but using PCA or Varimax instead of the ICA, but our results didn't improve. Thank you very much. That's it from me.